Oh, we have some
Hello
people
to
here already.
everybody. I think people can unmute themselves as well, right? I think at the most we might be around 20%, 25. So as we warm up,
I was
people
going to
can
say,
introduce
yeah,
themselves.
I can see MSF Sana Watson specialist. Good morning. Moise, good morning. Andre as well. Good morning, Andre.
Good morning, Paul. Good morning, Maite and everyone.
Good morning,
Good
Paul.
morning.
Good morning, everybody.
We have Theodore as well. Hi, Theo. How many do we have? 10 people so far. Is everybody okay?
It will be time to start. Maybe 1-2 minutes, then we can start, no?
Yes, perhaps. Let's see if I can call Aurora. People that have not registered. Aurora. Yeah, okay, see. Request attendee. Who is Brian? Who is the person under Brian?
Hi, I'm Brian Watt. Just in the pool.
Okay, sorry. It's because there's sometimes these
You're
sort
welcome.
of phishing things.
Thank you.
Yes, thank you.
Super welcome, Brian. Glad to have you along. I hope you enjoy the presentation and have some nice questions. Hi, Theo. Theo, good morning to all. Feel free to write a chat if you want to say good morning and things like that. If you have any questions for Olivier and stuff and you can't do it by voice, please feel free to write in the chat and we'll monitor the chat regularly and update Olivier during the presentation if any questions arise.
Let me find, because some people have problems to join the meeting. So let me copy the link, the event link.
Aurora's here and Bukabu has arrived. Good.
I think if people have challenges, it should be the link.
Good morning, Olivier. Good morning, Paul.
In case people have
Good
challenges.
morning. Good morning, Rawlings.
So let me
Nice
just
to see you, Rawlings.
Yeah, Aurora.
Hey, Rawlings. Good morning. How are you?
Good morning. Fine, thank you.
So guys, perhaps in the next 1 minute, we should be starting at 5 minutes past the hour. And thank you for joining. Maite, you may want to share your screen.
Let me just share it in a different way. Just my screen directly. Please let me know when you see it, yeah?
See it well, Maite. Very good and clear.
Okay, can we see Maite's screen? Unfortunately, I am not seeing Maite's screen.
Yeah, I can see it is visible here.
I can see it loud and clear.
Okay, then I would go from my screen and then Maite is projecting. If you guys are seeing, then that is fine for me. Welcome to everyone to this webinar series. It's part of the webinar series which we started, I think, a couple of months back, where we did 2 sessions, one on borehole constructions and another one on pump testing. Following those sessions, one of the topics that was raised as a possible topic that could be looked into is pump dimensioning. So we decided to look into pump dimensioning for you guys, and let's hope this session we will be able to bring you the insights you will need for that. Next screen, Maite, I think you're in the second screen with well construction, pump testing, pump dimensioning, correct?
Pump dimensioning, yes. Session 3.
Yes. So we are not going to make us experts of pump dimensioning, but the idea would be to push us to understand the basic considerations that need to be taken into the basic aspects that need to be taken into consideration when doing pump dimensioning. I am Olivier Camto. I'm one of the MSTs for OCBA, and it's my pleasure trying to guide you through this webinar. Table of contents, Maite.
Go ahead.
Great. So the idea here would be to talk about why we do pump sizing and what is pump sizing. Is it just an arbitrary thing that we should consider when we have to pick a pump and we pick anyhow? What are the key concepts we need to accurately size a pump? How do we actually do pump sizing? And we are going to show you some manufacturer tools that will help with the exercise of pump sizing, because as we would see slightly ahead, manual pump sizing can sometimes be a little bit trickier than more straightforward as it seems. Next slide, please. So the key learnings we are hoping to bring to you, as I've already mentioned, is to understand what are the basic principles that we need to consider, understand the fundamentals of pump sizing, and then get into feel of the aspects of the key concepts which we need for pump sizing, which are the flow rate, the total dynamic head, and a little bit of how manual pump sizing can be done. But again, in the end, be able to navigate a couple of manufacturer softwares that are existing and which we in OCBA are kind of using now for our activities. Next slide, please. So the first question, what is pump sizing? That's the first question we are asking. I'm still not seeing how the screen is, but this was intended to be a question which I'm asking. I don't know if it's, can you see the information
We have
on the screen, Paul?
We have what is pump dimensioning, and we have the picture of the pump.
Great. So can anyone tell us what he or she thinks could be pump sizing? You can just pick out, you may want to write in the chat. It could be one word, it could be what comes into your mind when we talk of pump sizing. Anyone?
Go ahead, Brian.
Go ahead, I think pump sizing is it's like determining the type of pump that will fit in a well or in a borehole, depending on the quantity of water we have.
Okay.
And which will also depend on the distance of the tank.
Okay, thank you. This is Rawlings, quantity of water. This is what I'll take, quantity of water, distance to the tank. Yes, anyone else?
Yes, in the chat you have Moise saying defining pumping rates, head and power requirements.
The head, the power requirements, pumping rate, this is linked to quantity of water, yes.
Yeah. Then you've
head,
got another one.
That is great. Power requirement, that is great. The head also, we can link it somehow to the distance to the tank. We would see a little bit how.
Yeah. Brian also commented to determine size most effective to meet demand and performance of the borehole. So
thank you very much, Brian. I like the idea of effective. To meet, I like the idea of the word effective, because we are looking for something that should be actually, as the word says, effective. In several aspects, cost can be one, performance can be one, etc., etc. So Maite, you may click. Going all from all of these information, pump sizing is actually choosing the correct pump that will match the system requirements. The system requirements that we are talking about here is the flow and the head of the system, but also that should be able to match the aquifer properties, because we may have system requirements that we need, but it may not match with the aquifer properties. So it could be okay for our system, but because we are extracting too much, perhaps the aquifer can have a problem, and then in the long run, we don't have the water that we need to satisfy our system needs. What is the reason for pump sizing? Why we do this? Mainly because of efficiency, or to ensure efficiency, to ensure cost recovery, and to ensure reliability. We should not go and buy a very huge pump that will not serve our purpose. Meanwhile, we needed just another smaller pump that could have been a little bit more cost effective. Or we should buy pumps that are most efficient based on our system needs. So there is a risk with pump sizing, and the risk that we often encounter is that we can either undersize our pumps or we can oversize our pumps. Oversizing our pumps, oversizing our pumps will entail high cost to purchase, high flow pumps for smaller system demands, which is, we would agree, this is not very good. And high head pumps for lower systems will cause increase in flow at tank level, but can also cause the dry run aquifer properties inside of the borehole. And if we have this, it can lead to burnout. Almost a similar thing for undersized pumps. Here, we would have pumps that would probably have to overwork their capacity if they need to meet our system needs. So we really have to find a way to be able to size our pumps to get what would be closest best to what our system requirements are. There is no one pump solution for any borehole. We can have several options that exist in the market, several kinds of pumps that we can use in the market. But the idea is to be able to pick the one that will be closest to the system requirements, but also best in terms of efficiency. So some common mistakes which we generally see when we want to pick pumps, when we want to size pumps for our uses, are generally picking pumps only by flow and probably ignoring the head losses So that's that. Next slide, please. Yes, in this next slide, we are seeing, I think, an image. Here, the idea is just to list some key parameters which we need to consider when we are sizing, when we have to do pump sizing. So yes, just kind of listing these parameters. You should not be seeing them, but can you tell me what you think is one or two? You see the image is labeled. No, I'm not sure. I don't know if it's very clear for you, but it's labeled 1 to 9. Can we guess what could be 1, 2, 3, 4, etc.? Number 3 is already given as the dynamic water level. That's kind of a hint.
1 is the actual depth of the well.
Thank you. That's correct. 2, 4, 5.
Number 2 is the water table.
Water level. Correct?
Yes. Number 3 is the pump, level of the pump, the pipe picking water from the pump.
Not really. Number 3 is going to be what we call the dynamic water level. Okay. When it comes to that, is the dynamic water level or the pumping water level. 4.
The horizontal distance between the pump and the water tank.
For horizontal distance between pump and water tank. Wonderful. Thank you. This is Bangi. I think it's Miriam, no? Thank you. 5?
Yes.
Will be the vertical height, the vertical distance between the pump and the foot of the tower. 6 will be the vertical distance from the foot of the tower to the tank inlet. 7 is the pipe, the type of pipe. 8 is the size of the pipe. So 7 and 8 are almost similar. It's the pipe and the size of the pipe. 9 is the tank volume. So of all of these 9 parameters, 6 of them, we would have to consider 6 of them when we need to size the pump. And the 6 of them, which are 3, 5, and 6, all of these, when we add them up, you would see these are kind of geometric heights. We would add them up and call them, and we term them what we call static head. So this is something very vital for what we need. I think Moise spoke of head when we were defining pump. But the static head is just a component of the head. What we need when we want to size the pump is the total dynamic head, which is a combination of the static head, but also what we call the friction losses that occur in the pipe. And that is where the size of the pipe comes into play, the type of the pipe comes into play, and the horizontal distance between the pipe, the pump, and the tank inlet. So 4, 7, and 8 will help us to have what we call the friction losses. 4 being the horizontal distance, 7 being the type of the pipe to be able to know what we to be able to determine the roughness coefficient, which would be used to assess this, and 8 the size of the pipe for velocity and things like that. So again, we saw this in August when we were talking about pump testing and stuff. One point to note here is the pump must, when we are considering pump dimensioning, the pump should always be installed below the dynamic water level. That's so the dynamic water level, in other words, the pumping water level is the level that the water is going to attain inside of the borehole when we are pumping at the pump rate which we intend to extract water. Next slide, please. So the key concepts here, as I was mentioning, that have to be considered, we would have to consider first the sustainable yield. This, we will not talk much about this. We spoke about this in the session 2 of in August, I think, where we spoke about pump testing and how to determine the sustainable yield or the safe yield of the borehole. Then the next aspect will be the total dynamic height. The total dynamic height, sorry, I put total dynamic height here. Well, they are similar things anyway. As we saw, one slide behind is going to be the sum of the static water level, so the geometric distance or the geometric height from the pumping water level up till the tank inlet, plus the friction losses, and eventually, when we would see in the next slide, probably some people would want to add what we call residual losses, but this is not very common. Another thing which we would have to consider is the pump performance curve. All of the pumps that we have in the market, when a manufacturer produces a pump, this manufacturer will have to produce the performance curve of this pump. And this performance, for each pump, there are several curves that exist, and these curves go for different parameters. Mostly the rated flow for which they designed that pump. The rated flow, the total head that this pump should be able to carry, or the rated head, and sometimes also the power of the pump. So that's that's what we need when we have to consider pump dimensioning, especially if we have to go for manual pump dimensioning. And another aspect to consider is the power source. I think all of these aspects were mentioned a while ago when we were defining pump dimensioning. Another aspect that we need to consider will be the power source. Are we going to run on grid power? Are we going to run on generator? Are we going to run on solar, etc., etc., etc.? These are key concepts, but then we will not forget other concepts like borehole diameter, which is very vital, because you can have a borehole of 4-inch, and you, without considering that your borehole is 4-inch, you go acquire a pump of 4-inch. For example, you would agree with me that it's going to be very difficult for this pump to fit into your borehole. So it seems little, but it is very important to consider this and always check when we are going for pump dimensioning. Next slide, please. So in this slide, I think we would have to talk about the total dynamic head, which we have already seen. And we say here the total dynamic head is going to be the sum of the static head, which you see. I think I tried to annotate it red. I don't know if you guys can see. Is the vertical distance from the pumping water level or the dynamic water level up to the inlet of the tank. We have the friction losses from the pipes and the fittings. Very important to note the fittings also that cause friction losses. And sometimes the friction losses from fittings could even be very, very, very high, so should not be neglected. And as I was mentioning a while ago, what we call residual pressure, it's not very important, this factor, but yeah, some people would want to ensure that they have sufficient pressure that is entering into their tank, and they can decide to add a residual pressure. Generally, it's about 1 bar or an equivalent of roughly 10 meters of head. That's that. So I would pay attention here to the friction losses, which you don't see on the image, but is associated to the orange line that we find here. And here in friction losses, we talk of two kinds of friction losses. We talk of the linear friction loss, which is the friction loss that occurs inside the pipe, and it's characterized by the pipe diameter and the pipe, the roughness coefficient of the pipe, so the pipe material. This is generally calculated using, there are several formulas in hydraulics which are used for this. We are not going to go into the details of this, like the Darcy-Weisbach formula or the Hazen-Williams. And as I said, dependent largely on the pipe roughness, on the flow velocity inside the pipe, or the diameter of the pipe. But equally, we have the punctual losses or the singular losses. Sometimes you would see like that in literature, singular losses or punctual losses, which are generally losses that occur, like for example, in valves, in couplings, in the teeth, in the elbows that you have in your fittings. All of these junctions that you put inside your pipe, they cause another kind of loss, which is called the friction loss, which is called the punctual friction loss. Sorry. So this one is sometimes it's calculated, but very, very, very challenging to calculate if we have to do this, because if you have a pipeline, say for example a pipeline of 5 kilometers, and you have, I don't know, 100 different bends or something like that, to be assimilating the friction loss of all of these individual components becomes very challenging. So most at times, this is associated as a percentage fraction of the total linear losses is generally associated to calculate what we call the friction loss, the punctual loss, sorry. And in literature, this can go sometimes from 5% of the total linear losses up till about 20%, 25% of the total linear losses that we can use for the punctual losses. This is very easy to talk about doing these calculations, but in practice, what we use more often in practice and in the field to determine the linear losses, is what we call the log scale or the nomograph. There are other tools that could be used, but that are very challenging as well to use. So I would present here just the log scale or the nomograph, which is a ready-to-use tool and a relatively more easy tool that can be used in the field. And what does this nomograph or log scale entail? You see it, and it has 4 entities. I'm sure that's what you guys are seeing on the screen, because I'm not seeing your screen. I don't know why, but it has 4 entities. The first one is the internal diameter of the pipe. The first line on the left is the internal diameter of the pipe. The second one is the flow. So it's going to be the rated flow that we intend to pass through the pipe. I think this one is a flow that we would have calculated. The third is going to be the velocity that is inside of the pipe. And then on the last one, we have the losses. We have the linear losses per 100 meter length of pipe. You see, so any figure you read on this value is the linear loss in meter, is the linear loss in meters per 100 meters. So when you get this, you would have to convert it to with respect to your total length of pipe. So how do we read this log scale? To be able to read this log scale, we need at least 2 parameters to be able to read the rest. And one of the first parameters, or 2 of the easiest parameters we usually have are the internal diameter of the pipe, or if we are still sizing the system, we can go from iterations. We like choose a particular pipe diameter which we intend to work with. But one thing we would always have more often is the flow, is the system need, is the flow that we want to run through the pipe. So this is read in a way. How do we read it? We have to come to the scale for the internal diameter. We identify the diameter that we are looking into. If it's 70, for example, we identify 70. We come to the scale for the flow and we identify the rated flow which we want to pass through this pipe. Once we have identified this value, you note here the flow, we have it in meters cubed per hour and in liter per second. So we have to be very careful with conversions and stuff. One of the challenges which we sometimes have with manual dimensioning, because a small mistake with the dimensioning, with the dimension can cause a very can lead to a huge error. So we have to pay special attention to the dimensions, the flow we have in meters cubed per hour here on one side of the axis, and on the other side in liters per second. The internal diameter we have here in millimeters. So once we have identified the internal diameter and the flow, with a meter ruler, we can trace a line from these 2 points that cut across all the 4 different curves. So it should touch the point 1, it touches the point 2, and then you extend this line that cuts across the velocity scale and equally the linear loss scale. And that is how we can easily read the log scale or the nomograph. One thing to pay attention when we are talking of water flow in pipes and hydraulics is the velocity of water inside of the pipe. And it is always recommended that we should have velocities that go between 0.7 meter per second and 3 meter per second. In our scale, we see it goes from 0.2 to 5. If we draw and we see that we are in a scale of 0, we have, for example, 0.2 meters per second, I would strongly recommend you should readjust one of your parameters so that the flow, the velocity should increase. And in this case, given that the flow is, I would say, standard, is rated, we cannot move the flow, then we should consider moving the velocity. Reason being that velocities of less than 0.7 meter per second can lead to deposits inside of the pipe. And on the other hand, velocities of higher than 3 meter per second can lead to erosion inside the pipe. When I talk of erosion, I'm talking of scraping of the walls of the pipe and phenomena which we call like water hammer, which generally happens with water hammer is when you hear the pipe vibrating sometimes a lot. I don't know, you may have heard in some houses, you hear the pipe sometimes when water is flowing through the pipe, a serious vibrating sound or some hissing noises inside the pipe. That's what we call water hammer. Next slide, please. So in this next slide, again, is still just talking a little bit about the total dynamic head and saying this is a very key parameter which we have to consider when we are talking about water, because we have to move water from one point, which is the pumping water level inside our borehole, to one point, which is the inlet of the water tank. So the water has to move this distance. If we have to move it over a 1 meter distance, the power we would need is going to be less than if we have to move it to 3 times the distance. It's very similar to, I put a bag of cement, it's very similar. If you have to carry a heavy bag of cement, you need more energy to be able to carry a heavier bag, a 50 kg bag of cement compared to a 1 kg bag. It's practically the same the same thing that happens with water. If we have to move the water from up to 8 meters of total head, for example, we will need more energy, we will need more pressure, and it's pressure that we use to move the water compared to if we are moving the water just 20 meters. So in water systems, we talk a little bit more of pressure because that is what we would use to size appropriately the power that we need for the pump and eventually the generator, the hydrostatic pressure. Next slide. Voila. So in this slide, we are talking a little bit of manual pump sizing, and the idea here is to give you the key 4 steps that we should consider when we want to do manual pump sizing. Step 1 is to determine the system need. Step 1 and 2 are to determine the system needs. Step 1 being the safe yield. And as I mentioned a while ago, this we had spoken a little bit about in August when we were doing the pump test and we were determining the safe yield of our borehole. So that is pump sizing starts right from this aspect. Pump testing, which is a very vital point, which we would always recommend to our friends in the field when putting in place new boreholes or when considering to size the pumps, to do the pump sizing, to be able to choose this. The second step that is very vital as well is to calculate the total dynamic head, which we have seen a while ago, and it is the static head. It is the sum of the static head and friction losses. And some people will add this pressure loss or residual pressure or miscellaneous pressure just for security margins. This is more for security margins, so you should not pay much attention to the pressure. If your friction loss is properly calculated and your static head is properly calculated, you should have a system that will be able to give you the water you need. Then after this, you would need to check the pump curves, and on the pump curves, that is where the bulk of the work happens. It looks very straightforward, but most at times it may be challenging. And I'll ask this question like just vaguely. Of all of us who are attending now, how many of us have experience with reading pump curves, or how many of us feel confident when exploiting pump curves?
So just put your hand up.
Just put your hand up to say you're confident. And
Maurice has got his hand up. Anybody else? Another one? There's 2 people.
Is Brian okay?
And Brian.
Voila. So that's it's a very challenging issue that sometimes we face. That's one, to read and understand the pump curves, but also sometimes getting from most of our local manufacturers may be challenging sometimes for them to give us the pump curves for their pumps that they are selling. So if you do not have this, it could be a challenge, because you may have a system that, for example, I would say something stupid, that is 9.4 meters cube per hour and 63 meters of head. But the pumps that you have, for example, are rated 13 and 60. So it starts getting challenging as to, do I use this pump? Do I not use this pump? And all of these kinds of things. So key parameters that you should check when you're exploiting your pump curves, like what you have on the screen here. I'm not sure how clear it is. We would have the top curve on the x-axis. We have the flow. We have the flow that has been used for this pump. In this example, I am using an SQ5 pump. In this example, then on the y-axis we have the total head. Each here is the total head. Then on the curve below, which is also very important, and sometimes you would have to read both of them simultaneously. On the curve below, we have also similar. We have the head, the flow. Sorry, you see the flow on the curve above and the flow on the curve below are similar. And on the y-axis, we have, on one hand we have the power, and on the other hand we have the efficiency. We would pay attention here to the efficiency, right? So when we are doing a pump dimensioning, we always talk of this concept of best efficiency point. And on our curve, we have to, on this efficiency curve here, you would agree with me, the best efficiency for this pump, this curve that is like a small dome is the efficiency curve, right? You'd agree with me that the best efficiency would be where you have the peak of your curve, right? So the idea is you always check on this curve, what is your best efficiency point? And if the best efficiency of this pump, for example, is somewhere between 4.5 or 5, let's say something like that. If the best efficiency point is 5, then you have here the 5. You go through with the other curves above here, and you can choose which of the pumps you would need. Now on the other curve above, you have several other curves, and you may be asking why several curves. This is a curve with 15, 25, 35, 50, 60, etc. In some situations, here would be the rated head. In others, it will be what we call the pump stage. I would explain to you what is the pump stage a little bit later on, later ahead. So what the idea now is, you have to always look for, on this curve, the best efficiency point. It should match your system flow. So the flow of the best efficiency point should match your system flow, or should be, generally in engineering, we would recommend should be between 10 and 20% of the best efficiency point on your curve. So when you come up here, if the best efficiency point is 5 and you have your system, you have a flow of maybe 4.5 or maybe 5.2, okay, it falls within that range, you can work with it. And then you would now have to use this area, and then you see where your what do you call, the total dynamic head for your system is, where they fall. It could fall somewhere between two curves here, and then if it does that, you then have to choose now between the pump that is above or the pump that is below, which of them will be able to work properly for your system. So you would hardly find in your system where you would come, for example, and you would have 5 and it falls directly on this straight curve here. So you would always have a probability where you may have to take a pump that is a little bit bigger for your system, or a pump that is slightly smaller for your system, but it falls within the best efficiency range of the pump. There, you know you're working in a good in a good situation. If you take pumps that fall largely out of the what do you call, of the best efficiency point, then you would have challenges. And there is this other small curve that I have put to give you an example of the problems that you may encounter if you're operating outside of the best efficiency point of your curve. And you would see it goes from problems like temperatures rising inside of the pump, in the engine of the pump, rising temperatures. It goes problems like low flow cavitation. Cavitation is a very serious problem that happens in pumps. And what is cavitation? It's generally just the creation of air bubbles inside of the motor of the pump, and these air bubbles that will cause the wearing down of the bearings of the pump, the wearing down of the impellers of the pump, and then eventually your pump gets broken and you start wondering why. You have problems with the seal life and etc. 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 This is when you're far below the the best efficiency point. But if you're above the best efficiency point, also you still have problems on the bearings, on the seal life, and equally cavitation problems. So it's always very important to ensure that you identify your pump is working in the best efficiency point. So all of this, as I was saying, manual pump sizing normally should look easy, but there is a lot of things that can cause you to not pick the correct pump if you're doing your pump sizing manually. Some of them could be approximation of friction losses. If your friction losses are poorly approximated, then we saw a while below behind the friction loss that is poorly calculated, it will lead to a poor total dynamic head. It could be very low, it could be very high. And a low total dynamic head will mean that you get a pump that probably will not be able to cover your system. Or a very high total dynamic head will just mean that you're getting a pump that is not cost effective for your system. You could have gotten something cheaper and it would have worked for your system. Sometimes, as I was saying, the data curves for the manufacturer's pumps are not existing. And we find this with some of these ready-made pumps, which we find locally, where sometimes you would buy the pump. Most of the most of the suppliers we would find locally are more or less business people. Their interest is to sell their pump and to make their profit. But what happens after that, or how the pump operates, is not generally their case. So manufacturer curves, at least from my experience in a few places where I have asked for manufacturer curves, they do not exist. And when I even try to find them on the internet, it's very difficult. Only some of these big manufacturers have to have their performance curves that are on the internet. Sometimes also there could be human error which comes into play, and human error we were talking a while ago. If you consider liters per meter square, liters per second, sorry, rather than meter cube per hour when you're reading the log scale, or if you do a poor conversion of one of the units you have, it could lead you to wrong data. And then sometimes reading the poor efficiency curve is a little bit it's a little bit challenging. The idea for the manual pump sizing is that we should look for a pump that will work, but not necessarily sometimes at the best efficiency, because getting something exactly at the best efficiency most of the times will be challenging. So these are some of the risks of manual pump sizing. Next slide, please. Yeah. So in this slide, we have spoken about the flow needed. We have spoken about the total dynamic head, but remember we spoke about a pressure or the power that we would need to be able to move this water above from the pumping water level to the dynamic water level. And also we have spoken about the efficiency, which is the efficiency of the pump curve, the best efficiency. So this is very key parameters which have to be considered. And when working on the pump, we need to consider what we call the pump motor power, which we calculate as the pump hydraulic power divided by the efficiency of the motor, right? So the hydraulic power of the pump is calculated as the flow of the pump multiplied by the density and the gravity acceleration due to gravity and the height. Here we are talking about the height. Here is the total dynamic height, right? So you see the hydraulic power of the pump is directly proportional to the total dynamic height. So if we have a very high total dynamic height, then we would also need more pressure, more power to be able to move the water to move the water from the pumping water level up to the tank inlet. So here also I have put this image of a pump and the impellers that you see inside the pump. The idea was just to let us know that the impellers or the stage is actually what helps to move water from one point to the other. And if we need to move water very high distances, you will generally find in the pumps the number of impellers are very, very high. The number of impellers increase. So the pump stage is generally equal to one impeller. The impeller is these small round things here you see like extract of the pump. And for example, if one impeller pushes water, let's say 10 meters above ground, that is how this is designed, then it means a pump that should have, for example, 6 impellers will be able to have a nominal head of about a pump with 6 impellers would be able to have about 3 stages or about 6 stages, sorry, just something like that. So the more you see the impellers or the stages of the pump inside your pump, the higher the head of the pump, and the higher the head of the pump, this also means the higher the power or the pressure of the pump. Voila. Any questions so far? Or we continue?
Anybody have any questions for Olivier on what's he doing so far about the pump sizing and the impellers? We're about halfway through now, so everything's going well, I think.
Come on.
Go ahead, Olivier.
So, next slide, Maite. Here in the next slide, we would dive a little bit from manual pump sizing and then we come to software sizing. And just some key points to note about software sizing. We have software sizing would help to automate friction loss and also curve matching. So we would not have to be looking into, please excuse me, let me send this child away. 1 second, please.
Give us some opportunity to write a question or two in the chat for Olivier to answer when he comes back. Well, let's wait till he comes back. See a question here from the Sanawat's hand specialist, which is good. Can send us solving examples, especially about cavitations. Good question. And that was also supported by Juba Logco. We just everything a little, Olivier?
Yeah, it's fine. It's fine.
We just had a little question in the chat saying, could you send us some examples, especially about cavitations and I guess how to avoid them? But we can put that in later on. Okay.
Yeah, we can put that later on. Exactly. That's fine. Okay. Point noted.
Okay. Carry on, please.
Come on. So I was saying for software sizing, it should be much faster than manual sizing, and we should be able to, if we have the correct input, we should be able to automatically calculate our friction losses, and the softwares will generally help us to perform the curve matching and then give us more or less the pumps that fit closest to the best efficiency pumps of the pumps that they are going to choose. Manufacturer like Grundfos, they have like thousands of different pump curves. So imagine us having to go through, for example, 20 or 30 of them or 10 of them to be able to choose 1 or 2 pumps. It can be challenging. When we have to do that for one pump, okay, we may find the time to be able to scroll through and then go through all of their catalog because they have catalogs that sometimes are this huge. But when we have to do this for like 5, 6, 10 different pumps, then you would agree with me that this could be challenging. The softwares will as well provide you the exact pumps, the exact models with the performance and the efficiency data, and will consider site-specific parameters like the kind of power supply, if it's solar, the irradiation, etc. So as I was saying, if you have to go to run a scenario between 5 or 10 different systems, it will be better to do that with software sizing rather than doing it with manual, because it will be more fastidious. But as we say in computer jargon, garbage in is garbage out. So if we input wrong parameters, then we are sure we are going to have wrong outputs as well. So the input parameters have to be carefully selected. We are talking here of the flow, of the rated flow. We are talking here of the elements that will help us or will help the system or the software to be able to calculate the total dynamic head. We are talking of the solar, of the power parameters, etc. But equally, if you master only software sizing, it could give you a false sense of confidence. That is the reason why we decided to start with showing you the parameters, the key concepts, and how to go about this manually, before eventually going by software. Because you could go in with the software, you could think you understand what has to be done, but in the end you generally do not master it, and then voila, you can face challenges tomorrow when you do not have the software. Then I will go into specifics for solar. Solar being the one reason being, this is one resource that we have free of charge and which can be exploited. And a lot of things in the world now are gradually going towards solar. So the water industry as well is going towards this, and harnessing solar energy to power pumps is increasingly becoming a topic of the day. Now, solar software sizing depends on a couple of parameters, which I'll just want to share briefly with us here. The location where we are on the Earth. The location generally will oscillate with what we call the irradiation. If you're in a very cloudy place, the irradiation there may be very low. compared to when you're in a sunny place. So if you're in Switzerland, for example, the amount of irradiation or the amount of sunlight power you can generate from the sun may be very low, for example, compared to if you are in, let's say, Chad or Sudan, for example. So the location of the Earth is very important. The time of the year and the day as well is very important. When there is cloud cover, you will not be able to have solar power. In the night, you will not be able to have solar power. So these aspects also are very important. So these have been associated into what we call peak sun hours. And peak sun hours, I don't expect us to be able to calculate peak sun hours. There's a lot of databases that exist around the world that give you peak sun hours for different locations in the world. So what are the peak sun hours? Are actually the period of the days when we have the highest irradiation coming from the sun on a given solar on a given Earth surface. You see, so it's the cumulative daily solar irradiance that we have on a particular surface of the Earth during one day. And it varies from place to place in the world. As I mentioned, it can oscillate from, for example, 4 or 3, even 2 hours in some places of the world, up till about 7 or 8 hours in some places in the world. So in an area where, for example, the peak sun hours is maybe 2, 3, 4 hours, that is not a very feasible solution to consider a big pumping scheme that should rely on solar. You see, so this is something that is very important that has to be considered if we have to consider solar pumping. Then another issue is where we are on the Earth, as I mentioned. So when we are sizing for solar, if we are in the northern hemisphere, then we have to orientate our solar panels should face the south. That is obligatory. It should face the equator. That's what we are looking for. Wherever we are on the globe, when we are setting panels, the panels should always face the equator. So if we are in the northern hemisphere, it should face the south. If you are on the southern hemisphere, it should face the north. But again, and importantly, the tilt angle of the solar panel is very important. And we are giving a minimum tilt angle of 15 degrees. This is so that it should be able to do self-cleaning. So all of those countries that are around the equator, I will take examples like Chad, Cameroon, where I am right now. If we have to install solar panels here, we would have to tilt them towards the 15 degrees at least, so that at least there's a possibility of self-cleaning. But if we go to higher latitude areas of the world, say, for example, Switzerland, or for example, in South Africa, right down towards the South Pole, then the tilt angle should be equal to the latitude of where you are. So these are parameters that we would have to consider when we are doing a solar pumping. Next slide, please. Then in this next slide, I am talking also about the amount of water which we pump. A couple of slides back, when we were talking about the manual pump sizing, we were talking about the amount of water which we pump per hour, because that was what we were looking at from our safe yield. The amount of water which we pump per hour, which is our safe yield, which is what we need to extract from the borehole. That's fine.
Olivier,
1 second.
Olivier,
Oh.
yes, the image is the solar.
Yeah, just click. Sorry, just click. The next one, the next image will come. I'll come to the solar panel. Sorry. Come on. So I was saying we have to look into the peaks. We have to consider when talking about water. We are talking for solar. We are talking about amount of water which we need in one day when we have to size using solar, and not the amount of water we need per hour. The reason being, as I mentioned, we are working with the sun, and you would agree with me, the intensity of the sun that we feel even on our heads is not the same throughout the day. In the morning periods, it's lesser, and when we go towards midday, 1 p.m., it becomes harsher, and later on it starts dropping again. So harnessing solar power, it's kind of a curve. It fluctuates, it increases with time, and then it drops back again later on. So it becomes challenging if we have to go by meter cube per hour, because we do not have a constant amount of pumping rate compared to when we are working with the generator or we are working with grid. And the more we have the irradiance, the more the power increases. So the power that the solar system will be able to generate in the morning hours is less than the power it generates later on. So we would have to think, when talking about solar pumping, we have to consider the amount of water we are pumping per day, but not the amount of water we are pumping per hour. It was just to clarify that point. And then coming on to the solar panels, this is also something very important. And if there is any of you here who has worked with me, each time we have had to do anything about solar pump sizing, I would always ask, what is you should try to get some key parameters of the solar panels which you have existing locally, because these are needed when we have to size the solar generator in the solar systems. So the key parameters which you have to check and which should always be on the manufacturer etiquette of the solar panel, we have the rated power of the solar panel, we have the maximum power current, the VMP, the ISC, this is the maximum power voltage, the short circuit current, and the open circuit voltage. Again, the idea here is not to make us electricians. No, the idea here is to be able to get the key parameters which we would need to feed into our system, into our software, to be able to give us a comprehensive system that we will need. If we make if during our sizing we use a solar panel of rated power 250 watt peak, for example, and the maximum power current of 1 ampere, and we go and during buying we buy solar panels of 150 or 200, for example, you would agree with me that these will not work. So it's very important that before sizing solar panels, solar systems, then there is some pre-work that has to be done beforehand to ensure that what we get is important, is what we would actually use, and we have a complete system. Sorry. Then there is one point which I want to make to just push here is solar panels. 10-20 years ago, solar panels were very expensive in the market, but nowadays we have solar panels that have the price of solar panels have become really cheap. And with that, unfortunately, we have also very good solar panels, and as with other products, we have very bad solar panels. So we encourage you to try to ensure that the solar panels which you are acquiring or which you want to buy are solar panels that should have been certified. And there are several certifying programs that exist worldwide. And here I put, for example, 2 websites where you can, if you go, you can get the certification number of the solar panel that they are promising you or that you may have to buy, and you can input into these databases, into this website, and it could tell you whether or not these solar panels are certified and whether or not you could use them. So it's just like quality control to ensure that what we want to use is exactly what is going to be of good quality. In Okba, for pumps, for example, we have 2 brands of pumps which we are recommending for this for submersible pumps, for example, because these ones can be found almost everywhere. But for solar panels, it's a little bit tricky. If we have to recommend a particular brand of solar panel, then it could be very challenging, and it would need that each time you have to acquire a solar panel, you may need to start looking for what they call international orders, and this could be time consuming, this could be time wastage, etc., etc. So this is kind of an easy way to check and verify that the solar panels which you may have locally around you could be good solar panels and could be certified. Next slide, please. So in this next slide, just telling you, as I was saying, we have 2 brands of pumps which we recommend for Ogba. We have the Grundfos, we have the Lorentz. One particularity in that is that Grundfos is, I think, is a Danish firm, and yeah, they produce their pumps in Denmark and stuff. And we recently, I don't know, some of you may have seen, but MSF recently signed a partnership with Grundfos, giving us some privileges on some of their pumps. So they have a sizing tool which is accessible, which is online. So for you to use it, you would have to go to the Grundfos website and you input your parameters and stuff. We are going to try to navigate that a little bit. Grundfos, you can size both solar pumps and conventional pumps, normal grid-powered pumps. Lawrence, on the other hand, the advantage with Grundfos is you have the application installed and you do not need internet to do your sizing, so you can do your sizing wherever you are. The challenge with Lawrence is the software is not easy downloadable. You need some access, access some credentials before you would have access to download the software and stuff. So that's a little bit the challenge with Lawrence. And Lawrence is specialized only on solar pumps or solar pumps and hybrid pumps, you see. So that's a little bit the challenge, the difference between both. So after doing all of this, there is a small example which we are going to do for a couple of minutes, just for us to see if we grasped the ideas of the manual pump sizing. And then after this, if we can do this in about 10, 15, say 10 minutes. After this, I would go through rapidly the softwares for Grundfos and Lawrence, just to give an idea of what they look like and how they can be applied. So in the example, we have the example. I think you have all of the parameters that are stated there, and I am saying we should ignore the residual pressure and we should consider 10% of linear losses as punctual losses. And for that, I'll ask you to rapidly calculate the static head, the friction losses, the total dynamic head, and probably to identify from the pump curves that you would have to try to choose the pump curve. Maite, you may want to put in the chat the pictures, the documents that I shared with you for the log scale and the pump performance curves, so that it could be used. Is that okay?
She's doing it at the moment, I think.
Oh, let me see. Maybe I can try it myself. Okay. Let me see. I can put it.
You can put it this way. I have to change user.
Okay, let me put it then. Okay, something is not right here. Okay. Wow, something is happening here now. I'm not sure why this is happening.
At the moment, while you're watching the screen, which Maite has up there, you can look at the static head, because you can see what has to be added together to give you the static head. You can also look at the example of friction losses for the pipe lengths and things. The other ones you have to wait until we can get the tables put in place so you can have a look at the calculations.
It's really strange, yeah.
Also, there's a comment in the chat that Moise has emailed Lawrence last year and they easily provided me with the credentials for the software. So everyone can request it easily if needed. So as well as having the access to the ground force thing, there's access to the Lorentz one as well.
Okay, Maite, I don't know why, but I'm not able to load this thing in the chat. I'm surprised. I don't know what's happening. Okay, Maite, you can stop sharing your screen. I'll share my screen so that you can see the example. And voila, while you try to load it.
Yeah, and then I will share the exercise with all the numbers. Yes, in the chat. Yeah, it's quite straightforward to ask them for the permission to have the software. So you can do it directly or you can contact either of the MSTs to get it. Or Lorentz.
Can you see my screen?
Not yet.
Yet. No, it's not coming yet.
Ah, something's
But I should
appeared. The questions appeared in the chat.
Yes, I sent that, so people has the example in the chat.
So if we have another 2 or 3 minutes to see if we can get the table to them, the tables they have to do the calculations with because they haven't got the table. You're managing to get the table to them, and the
Yeah, I think Maite is trying that now. I'm having some challenges.
No, oh, okay. Where did you share it?
I sent it to your Teams. I sent it to you on Teams. A message.
Yeah, so I have to disconnect from this one and go to the other one. I hope it doesn't crash the meeting, yeah?
Yep. Can you see? I'm sharing my screen now with the example. I don't know if you guys can see.
no. I think you're on a different
connection.
Nothing's coming from there.
Oops, sorry guys.
We've got about half an hour
Technology.
left. We've got about I know. We've got about half an hour left, Olivier. How long do you want to wait before we start going through the solution?
We can start. The thing is, they need the log the log scale to be able to answer the friction loss. The first one we can already have that. The static head, if someone has already done the static head, then you can tell us what you have as an answer.
Okay, so if someone's got an answer for the static head, let's see. Static head. Theodore's put in an answer for the static head, which is H3 plus H1.
Okay,
which is
let's have a couple more if possible.
Meters. Any other things for the static head? Any more for the static head? Asia Watson 46, and you're working out. Where's the 46 come from? From MSF Asia Watson. Anything else for static head? Any other ideas for static head?
I cannot also add chats, documents in the chat, Olivia.
It's strange, no? This is the first time I'm
I
having
can
this
just
happening.
do to me as well. I'm not sure.
So Brian has the same as Theo, which is 64. So people tend to enjoy Theo's answer for the static head.
Okay.
If we can't get the screens up, Olivier, then we can go through the answer a little bit at a time, and you can show them how to do it on the screen.
Okay. Yes, we can try. So yes, for the excuse me, for the static head, I don't know, Maite, you should be, if possible, you should share your screen again. The static head, yes, we said the static head is the geometric distance from the pumping water level up till the dynamic from the pumping water level or the dynamic water level up till the tank inlet. That is what we saw as the static head, right? So from our graph here, if we take from the pumping water level up to the ground level, and then from the ground level up to the tank inlet, that is the height we should consider as the static head. So I would agree with Theodore. The static head is effectively 64, which should be H2, which is the dynamic water level, as I said, the pumping water level, and the H1, which is the height from the ground at the pump surface up till the tank inlet. You notice here we are talking of the height from the ground at the pump surface. So you may have a confusion, and yeah, I could have actually made it a little bit more confusing to have given you the height from the foot of the tower up to the tank inlet and the other height below. So sometimes you may have to pay attention to that. When we are talking of all of the vertical height that.
Oops, and now he's frozen. Here we go. Maite. Can you take over the
static head, sorry.
Okay, Olivier, just say that phrase again because you were frozen out. You're explaining there's two different answers for the static head so far. One says 46, the other one says 64. And you're saying it is H3 plus H1.
Right. So that's a little bit what we need to consider. Now, the next thing which we have is the friction loss. And it's unfortunate I'm not able to share with you the normal graph or the log scale. That is what we were trying to sense that you could try to map that out yourselves. But I'll see if it's possible for me to share it on my screen, and then I would like one of you to help interpret what has to be done. I don't know if it will be able to, if I'll be able to share from my screen. Maite, could you share from your side? Because it's like you guys are not. Are you seeing my screen now? Can you see my screen?
I don't think it's your screen. I think this is Maite's screen. There you go. There's an graph.
No, my screen is showing with the example.
Okay, this is yours. We have the graph now on the screen.
I'm sharing. I don't know if you can hear me, but then you can share it. But like I can stop sharing myself from my side. But now I'm sharing the log scale.
At the moment, we have the graph on the screen. So talk through the graph then, because it's there in front of the screen. You've got the internal diameter, you've got the flow rate in meters cubed per second, you have the velocity and the losses.
Okay, so from the example we are having, what is the first parameter we need to consider to estimate the friction loss? What is the first parameter? I think we have that.
Anybody got an answer for him? What's the first thing we have? Pipe diameter. Brian says the pipe diameter we have.
Great. We have the internal pipe diameter, which is 100 millimeters, correct? Correct. So we have the pipe diameter. What is the second one? It is not given on the example, but if you were listening, you would tell me the flow. Thank you, Moise. And the flow in this example is 30 meters cubed per hour. Oops. The flow in this example is a 30 meter cube per hour. So what do we need to do? We need to go with the pipe internal diameter. We need to go with the flow, and we go to the normal graph. But again, there is something that is important that we have to consider. Can somebody tell me what that is? It's related to the pipe.
Materials.
Material of the pipe, the material of the pipe. So we need all of these things to be able to go to the normal graph. Now, when we go to the normal graph, are you still seeing the normal graph?
Yes.
Yes. So when you go to the normal graph, what do we have to put? We need to put the diameter of the pipe. We have to mark it on the scale of the diameter of the pipe. We also have to mark the flow. The diameter is 100 millimeters. The flow is 30 meter cube per hour. And we have to trace a straight line between that and
yeah, Maite's going to try to do a straight line with a pencil.
Okay.
There you go. It's almost a straight line. It's good enough, Mighty. Well done.
Mm-hmm. Voila.
So what you've done, you've got a red line across there. Go ahead, Lydia.
So what value do we have for the friction loss per 100 meter of pipe? A small correction on the log scale you're having. On the log scale, where you have it written metallic is actually plastic, and where you have it plastic is actually metallic. So you may want to you just have to invert that in your reading. Sorry, but yeah.
Funny.
So what value do we have? I think we have a value of, for plastic, if it's drawn properly when I was doing, it's approximately 1.1 meter per 100 meters. Are we close to that? I'm sorry, I'm not seeing your screen, so I just have to.
Yeah, more or less, yes.
It's about 1.1 meter per 100 meters, correct?
Yeah.
And Theodore has done it better. Thanks, Theodore.
Ah, okay, so he already did, fine. So, okay, Moise also had 1.3, fine. So we are around that. We are around that. So let's go for 1.1. Let's assume it's 1.1. And now we have 1.1 meter per 100 meter. Can we now compute what we have as friction loss? Yeah, I'll keep quiet for a while, and I'll want you to give me what you have as friction loss.
So you should be calculating now
Anybody?
the friction loss. We're now no longer looking at the nomograph. If anyone has an answer for friction loss.
We have 1.1 meter per 100 meters of pipe. What are we considering? What do we need? We need to find the friction loss for 700 meters of pipe. So we have to convert 1.1 per 100 to the friction loss for 700. That is correct, no?
We're back on the main screen now. We have the answer for static head. Friction loss, anyone got an answer for the friction loss? If it's 1.1 meter for 100 meters, what's the friction loss for 700 meters?
Okay.
Have an answer there from Theodore.
Good. 1.1 per 100 times 700 plus 10% of 1.1. Very good. Thank you, Theodore. This is actually it. So, Maite, that is it. And if we compute this, it will give us 8.4. So remember we said the friction loss is a combination of the linear losses and the punctual losses. And in this example, I said we should consider 10% of linear loss as punctual losses, right? So I would go with Theodore. It's 8.47, which is 1.1, as Theodore has written, plus 10%. Moise 7.7, Bukavu, Watson 7.7. This is only the linear losses you have estimated. So when you add the friction losses, then it will go up to 8.4. So thank you. So the total dynamic head, therefore, in this case, as I said again, remember the total dynamic head, we ignore residual pressure. In this case, we are going to consider the static head plus the friction losses, which is 64 plus 8.4, which should give us something around 72.47. Now, we had to choose the pump, right? And the idea is to choose a pump which I had shared, but unfortunately it's difficult to send to you. I don't know why. So perhaps, Maite, you may want to put up the pump curve again. Put up the pump curve instead, and then we would see if someone can identify rapidly what pump may be suitable.
But now we can, I don't know which one I should choose.
Now we have the performance curve for the SP17 on the screen. So you're dealing with your 8.4 losses.
We have the 8.4 losses. We have 30 cubic meters per hour. Now the idea is which of these pumps that you have should we choose?
Have a look for the smaller head one, might I?
Yeah, just for a hint, I wanted to share this one has, I think I sent 3 pumps. The idea was for people to be able to go through, but now it's challenging. So you may just want to use my page, the
It's very fast for me.
For the SP.
It's very fast. Now I was just trying to get the ones that we have more or less the flow rate of 30. You said 30, isn't it right? Or am I right? 30 meter cubes. Which was the flow rate you said?
30, yes.
30, yes.
Use the SP30.
30.
SP30, might I?
SP30, which
Go up. That's it. That's it.
so we are in 30 meter cube. Wait. 30 would be
And the one that has the efficiency curve.
the one that has here. Below. And then the head, we're like around 80. Am I right? Olivia, I believe.
Yeah, so it's we are supposed to look on you're on page 3 now.
On
SP3050
page
hertz.
50, I'm in page 6. Is that page 6? SP30.
No, 6 is the chapters. Look below. The page number is below, close to Grundfos.
Yeah, so 52.
52, great. On 52, what we have to do now is the pump efficiency curve. What is the maximum efficiency of this pump? We see it oscillates. It is about what they call. It's about 75%. No. The peak of this curve, if we look at it on the efficiency curve, which is slightly below.
Yes, around, yeah, 75. Let me just put on this.
At this efficiency, we have at the flow of 25 up till about 30, we are still within this efficiency rate. So our system need, which is 30, falls very well within the best efficiency point. Do we agree?
Yes.
Great. So if we now mark on the curve above 30 cubic meters per hour, we draw a straight line up and we find the intersection. How much was our total dynamic head? It was 72 or 73, more or less, right? So if we go from 72 and 30 cubic meters, we fall somewhere. Can somebody tell me approximately where we find ourselves?
People can annotate, I think, right? I'm
Oh.
not doing that.
The red line's a bit excited there. The smiley face at the bottom there. But have a quick annotation and have a little look on the graph I've got in front of you. If you go up the line, what do you find? Oh, there's a line. Someone's put a line in.
Not sure if anybody put it away. We began trying to use this annotation thing, and it's
Sorry, but I don't know why I cannot see your screen. So
At the moment, they've got the graph table out and people are looking at it to try and ascertain the crossing point. In the meantime, there was a question from Asia. Could you inform us the amount of elevation difference between the delivery point and dynamic water surface?
Yes, thank you, Asia. I'm sorry I don't have the name, but this is what we call actually the total dynamic head, the static head, sorry. The static head here, Sahe, is, as we said a while ago, if you look in on the diagram on the image, we have, it's annotated there, we have dynamic water level, and we have it H3 equal to 52. So the level between the pumping water level or the dynamic water level and the ground surface you see is 52 meters. Is that okay for you? Do you see that?
Sorry, it's like I'm trying to, it's complicated to keep sharing the one with data.
Oh,
So
sorry. Okay.
I'm sorry. If I'm going now to share just the slide, but keep changing from place to place.
Yeah,
It's
share just the
okay.
slide and continue.
You have it in the chat. You have it in the chat already, so he can look. I can talk with him from the chat, so that should be fine.
Ah, okay. So well.
So you can just continue with the pump curve. So Sahel, you see, we have from the pumping water level up to the groundwater level, that is the pumping water level or the dynamic water level. Then you'd see again H1, it's written height from the well surface to the delivery point. That is the figure which I gave you. So this is the point I was noting is you should always ensure that we are taking the total geometric distance from the water level or the pumping water level up till the inlet point. This is parameters that you in the field, when you're doing your estimations, you'd have to calculate. You'd have to actually measure them so as to avoid surprises. These are things the pumping test will be able to inform you on the pumping water level. And then when you have the pumping water level with the GPS tools, we can be able to calculate to get the altitudes of the pump, the ground at the pump at the borehole area, and also as well at the tank area, and then we can get the eventual height difference between these 2 points. So these are things that have to be measured. Here it's pretty straightforward because I've given the figures, but in the field, in practice, you would have to measure them with pumping test for the pumping water level, and then with GPS tools and elevation differences to be able to have the elevation difference from the tank inlet and the borehole outlet. Is that okay, Sire?
He's saying, based on his understanding, 64 meters. What we can do, we can talk to Saya later on if he's still having problems. Maybe we can talk to him later on after the meeting and have a little discussion on this, because we have 5 minutes left in the meeting.
Yes, that will be fine for me. After this, you can talk with me, Saya, and yes, 64, and yeah, we can talk about this, Saya. So that's fine. And then before that, I'll beg your pardon to extend 10-15 minutes more so that we can be able to look at the software sizings. Voila. So have we been able to get an idea of where the intersection of the flow and the total dynamic head on the performance curve is?
Sorry, Maite, could you please show us the entire pumping curves?
Mm-hmm. Mm-hmm.
Sacher, if you have time at the end of this meeting, Olivier can go through with you and you can talk later on the discussion. It's a very interesting point you make, and I'm sure Olivier will enjoy discussing with you after the session.
Sorry, Olivier,
Yes,
I have
we
a
will
question.
talk.
It seems that, yes, Olivier, it seems that it doesn't cross the maximum efficiency doesn't cross any curve.
Wonderful. So where do you find yourself?
Yeah, just above 50 the second, this second line between 105 and 5 and 50. So
okay.
So he's saying the
now
line doesn't
you find
cross
yourself
Olivier.
somewhere, right?
yes,
I'm
but
sorry, I
it
cannot see it.
doesn't
So
cross.
you find yourself between two curves, right?
Not
Below-
really. If like the
below
head
all
is
the curves.
around
not
80,
between
right?
the curves.
Below all the
We are
graphs.
70
Below all the
Below
curves.
all the graphs. Okay, Maite, then it means you're on the other curve. It means it starts with 150. There is the other curve just above. That was the exercise I wanted us to see if we're looking at it. There is the other curve above, which is the curve we should use then.
It will be,
that one.
yes,
There you go.
so
You
here
get-
we are in 30.
So you see, this is kind of
Now
the
you go up.
complexity with the manual sizing, because you may have something and it is not going to be what we need, right? So you have to look for the first curve and then look for the next one and then look for the third one, etc., etc. That was why I actually sent the 6, so that I was hopefully going to get us thinking. And I'm happy it happened like that. So I think now you have the correct one, right?
Yep, that's
I'm
better.
going to
That
move
was
it
good.
up so
And
we have in
it
the
was
heads
spotted by Brian as well.
properly.
Well done, Brian.
Yes.
So you can go up now
With
directly.
efficiency as well. Sorry. I think that should be good.
And now you'll be able to give us the number because it's nearer between the two graphs. It appears
Yes.
between the two lines
So
now.
it's between two lines, right?
Yeah.
Which of the two lines then do we does it fall between? So you just have to go up a little bit. You follow the line, and at the top of the lines we have a figure. You would see the figures go from 1 to 15 on this curve. So the two curves where you fall between, which are the curves?
So Bangui says 8 and 7. Between 8 and 7. Bangui said between 8 and 7.
Okay. Anybody else?
I would go for 6.
So that's the line,
Okay.
approximately the line might have drawn for the 30. So it's on that line.
Somebody, that one is not me.
Okay.
Oh, okay, sorry.
Sorry. Yeah. I'm saying, I was going to say, I understand somebody said 6, somebody said 8 and 7. That is fine. But I would suggest to check a little bit further, and then we are not drawing a horizontal line here this time around. We are looking at the curves that have already been plotted. When I was looking at this, I think we are between, on the contrary, we are between 9 and 10. You correct me if I'm wrong, but I think we are between the curves.
Just remind everybody what the numbers are again. The Q, as in the meters cubed an hour, is 30.
30.
Yep, and the other number we're looking for?
73. It was 73. Say 73.
73. So if you go across from 73 and the 30, you will get to between 9 and 10.
I don't know if you guys see it.
No, here.
That's between 9 and 10, is it, Maite? I think.
It is, yes, between 9 and 10. Yes, it's around here. It's a bit more on top of 10, but yes, around here.
Yeah, Maite's put the spot approximately
So
there. Yeah, that's right. That's okay. No, that's good enough. So it's coming out between 9 and 10.
So in practice, this will be the pump we should need to either of these pumps between 9 or 10. And it will be advisable, since our flow was 30, it will be advisable to take the 10, which is kind of the upper limit, rather than 7, rather than 9, which is the lower limit. But any of the pumps SP 30, 10 or SP 39 could serve our purpose. Yeah. So this is a little bit the challenge with picking the right pump when doing it manually. Are we agreed with this? Have we seen the point that is between 9 and 10, contrary to 7 or 6, which some people mentioned?
Yes, please.
Voila.
And this is 10.
That's fine. So, okay, is that okay?
Mm-hmm. Yeah. Now I'm sharing back again the exercise.
Voila. So that's fine. So this is generally how we have to go for this. The next thing which I asked was to be able to calculate the pump power. Maite, you may just pop that out.
Yes, I have that.
You may just pop that out, which shows how we calculate. Brian, yes, not to forget friction loss, otherwise your pump is small. I'm not sure I understand what you mean by this comment, Brian.
If you pick the lower one, I think he says if you pick the lower one.
If you pick the lower one, great.
You will have problem with the friction losses.
About, that's correct. If
okay, Brian,
that is what you're talking about,
that's
then
what you understood.
So,
okay.
Exactly. So wonderful, thank you. So you'd see here, I was just trying to calculate what is going to be the motor power which we would need for this pump. And from the calculation, you see we would need a 7.96 motor power. Now you can go for this as a homework. If you check on the internet for the SP30 brand of pumps, you would see these pumps have a motor power of about 9 kilowatt. So this is giving you an idea of the generator power which you would need to be able to run through the generator power you would need to be able to run through to be able to power the pump. Sorry. So that was just the idea for this. So I think this is clear. If you have questions, maybe you can ask now, or you can ask again later on, maybe bilaterally, so that we gain in time, and I can move forward. Is that fine?
Yes. Put your comments or your questions in the chat, and Olivia will go back through the chat afterwards to make sure all the answers are correct, especially the concerns of Sahir. See if we can explain to him. Go ahead, Olivia.
Thank you. So now, I don't know how we are going to do this. I needed to share my screen now at this point, but if I'm not able, that's going to be a challenge. Maite, could I try sharing my screen to see?
Yes, I stopped sharing mine, so go ahead, please.
Great. So I'll start sharing mine, and I'll share you the sizing page for Grundfos. You tell me, please, if you can see my screen.
Yes, now it comes. Yes.
Yes, we have.
Oh, you can see my screen. Voila. Okay, so this is what the Grundfos web page looks like. This is what the Grundfos web page looks like. When you would open the link I sent you, it will appear exactly like this first, right? You would see just the size product, and then you see size by application. Voila. So here we are going to take to size by application. This is what you have to take, and then eventually you select the application area. We will take municipal water supply, and then it would ask us to take the application, and we will take groundwater intake. We could have taken solar water solutions, but now we are taking groundwater intake because this is just the general the general one. And voila, we have here borehole installation. There's several options, but in our situation, what is best, what we have to take is borehole installation open tank. So we are pumping from a borehole to a tank that generally is closed, but is open to atmospheric pressure because there is kind of a breathing space inside of the tank, right? So we take borehole open tank because it's subject to atmospheric pressure. If we take closed tank, then this means it's kind of a pressurized system and stuff, but we are not looking into this. So our system will take borehole open tank, and then we would have what we have down here. So now we have to select the parameters, right? So the idea is to input the flow which we need. Remember we said 30 cubic meters per hour. We would have to put in the head, and we have two options here. If we are confident of the head which we have calculated, we can write the figure. But if we are not if we think we do not master that, then we can click on this small calculator button here, and then it will ask us some information, right? Now, probably this may answer some of the questions Sahel was talking about. There is the nomenclature sometimes varies. So in some places you would see static head, you would see lift head, you would see there's a lot of literature, right? So the idea is when you have when you're faced in a situation and somebody tells you static head, you should understand what is defined by static head or what is defined by lift head, right? So that is it. Now here you see here they say static lift above the ground, right? What is the lift above the ground? What is the water level we are looking at above the ground? It is 12 meters, right? From our example, it's 12 meters. And then the static water level, this I did not put because I don't need this one, right? This is the depth up to the water level in rest. The dynamic water level is 52, which is the water level from the ground surface up to what they call to the pumping water level. That is that. I put the 52. Test flow I don't put. The casing inner diameter, this is not very important for me. Then what is important now is we need to calculate the system friction losses. This is the next important point, right? And to calculate the system friction losses again, we can then click on this small calculator here. And here we have riser pipe friction losses and then discharge pipe friction losses. In our example, I made it a simple example where I considered the riser pipe and the discharge pipe to be the same material. In some situations, it could be different materials, and different materials mean different roughness coefficients, so perhaps different friction losses, or it could be different diameters, and different diameters also would mean different velocities, and then different velocities mean different friction losses as well. So all of these are things that have to be considered. But now here we have the riser pipe. And how long is our riser pipe? From our image, our riser pipe is 200 meters, right? The riser pipe is 200 meters. The pipe from the pump level up till the ground surface, 200 meters. So we would come to the riser pipe here, and we click on the calculator again. The material polyethylene, the inner diameter of the pipe, we said it's 100. You'll see from their drop-down list, they do not have 100. So I can put here manual input, and I put 100. The pipe length for the inner, for the riser pipe, it's 200 meters, right? That is what we have on the image. I'm sure you guys still have this in the chat, so you can confirm with me. It is H4. And then the riser pipe friction losses, we put a fraction of 1, let it calculate it. Suppose here we have to put between 0 and 1, so it has to calculate the friction loss. And then I click on OK. Okay, 1 second, 1 second, 1 second. The material is not good. I was supposed to use this material. Voila. This is the challenge now sometimes that we have with the Grundfos software. It bugs a lot when it comes to calculating these friction losses. So this is sometimes where we have to pay very special attention. In manual side, no, not manual, in a regular pump calculation, it has this issue for friction loss. But in the solar sizing, its issue generally is with the inputting of the solar parameters. That's a challenge that, in principle, Grundfos is having with their sizing parameter. So yeah, I'll try something else. I will not go for manual input. I would choose, for for example, so that we can see the friction loss, I will take this 96, which is closest to our system, and then I will ask it to calculate a little bit. And you will see now it should give us the correct the figure now. Now you see it has calculated the friction loss according to Grundfos of 2.4, right? Then we will do the same similar for the discharge pipe, the same pipe material, the same inner diameter pipe, this one. And then the length of the discharge pipe here, the length is 500 meters, which is the horizontal length from the borehole to here. L2 is the total length. That is why it is 700 meters. It is different. So here, the length here is 500 meters. And then an additional for single losses is it's 10. We said in our example 10%, and that is it. We would validate here, and we see what it gives us as an answer. 6.7. Okay. Okay, so you'd see Grundfos calculates the total head at 73.23. We calculated at 72. Remember, we used the nomograph, which is more approximative. They used the formulas and calculations, and that is why we have this. So we are almost similar. This is fine. 73, this is still good. So these are the two key parameters which we need to input. All of these other systems, these are when we want to consider particular configurations. This is not of importance to us now. Once we have these two figures, all we need to do is to start sizing. And then the software is going to give us everything, the different options concerning this system that will meet this system. It will give us the
Oh, whoops, a little bit frozen there.
Systems that we are seeing here now. Yeah, I think it's loading, it's turning and turning and turning. And you'd see, voila, 10 best matches. You'd see, so it says 10 best matches, right? So here we have the different options that Grundfos proposes to us. Here is the SP3210, not the SP30. And it gives different parameters, the power, the flow, the height, the what do you call, the efficiency, etc., etc., etc. So these are the different options of these pumps that you can use. You'd see it's SP32 10, SP32 11. Yeah, it's just some life cycle analysis which we do not need based on where it has been produced and all of these kinds of things, because it will depend on the product number. So now based on this, if we click on this, it will give us all of the information, for example, for this particular option with the pump curve, with the performance curves, and at the system points, etc., etc. And voila, you can see them, all of them here, sizing results, right? So it shows us everything here. This is the load profile. This is where we are, and all of it. It gives us the characteristics of just the system which we have mapped out, right? 73. It goes up here, and 30. This is where it is, and the best efficiency point is slightly above here, right? So this is it, and you have everything concerning this pump as you would want, and all the characteristics. So this is Grundfos, and you can easily pick this. You can, if you want, you print and stuff. We will not go into all of those now. Now, as I said, you can print from here. If we are done with this, I'll go back one step. It brings us back to the result page. And if we want to modify something in the input we put, we can do edit sizing, and it will modify, and then it gives us again everything we needed there. So this is this for Grundfos. Any question? No.
Looks all quiet. Go ahead.
Remember I said, yeah. So that is it. Now, if I go back a little bit to edit sizing again, and we come in municipal water supply, and then we take solar water solutions, and then we take solar system, right? We can take the solar system. Then we would have, you'll see the page has changed. And what does it start with? It starts with the location. Remember a while ago when we were talking about solar considerations, we spoke about the location because the location is very vital. They always start on the initial page. When you start, it will show you the location of where their factory is, a good marketing policy. But now it is for us to modify and put wherever we are. If we have the latitude and longitudes, we input them. If we know where we are, we can scroll on the map, for example, and choose wherever we want to go. You see they are right in Denmark. Let us choose, for example, Douala, where I am now. Voila. Let's take something around here. And you see Douala, it modifies the latitude and longitude automatically. And then we have to go, the power supply, let us go for a solar system alone. And then the type of pump is a borehole pump, we size by water volume. And we have to input all of these other parameters again. You remember a while ago, I said we are sizing meters cube per day, right? So you see even here, they have already put, we should put meter cube per day, and etc., etc. So if you come to each of the parameters, you would see what they have written: required water volume per day in peak season, static lift, the geodetic difference in height between the ground and the consumer or tank. And you can click on this information stuff. It can give you a small image to ensure that you are not mistaken with what you're considering. So you see here is the height between the tank inlet, you can see, and the height from the ground level where you have your borehole, right? The static lift above ground. And then below it, you have you have the dynamic water level, which is the water level as we saw a while ago below the borehole. Up here, you see the dynamic water level, which is a sum of the static water level and the drawdown. So it also gives you these illustrations that can help you to ensure that the parameter you are inputting is the correct parameter. So that is a little bit how it appears. And then the friction losses calculations is practically the same like what we saw a while ago. And the parameters which you have to look, some things that I want to ask you to pay attention to now is the month of sizing. Remember we said solar irradiation varies from day to day, it varies from time of the year. So when you're sizing for solar systems, you have to pay attention. Are you sizing, what application are you sizing for? Are you sizing for the best month when you have all of the sun, the best sun during the year? Are you sizing when you have the least sun? Are you sizing for, so this is up to you to choose, and then you have to input that here. You see, so for the area where you are, you should be able to check, and then it will tell you what period of the year corresponds to what to what sizing time. You see. So you see in January in Douala, this is information for Douala because my location I put, it gives me from January to December, it gives me the different irradiation values. And you see by default, it chose July because in July, in August, sorry, it has
Whoops, looks like a little hiccup again. He's trying to
6 horizontal radiation. In January, February, you have more, so you will have more water in this period. So that's just what it is. If you can have more here, then you will have. But if you size your system for January, then you may be having challenges in August to be able to produce the water you will need in August. So these are the things that you would have to consider when inputting here. Okay, that's that. And again, what I was saying about the solar modules here, they have their predefined solar modules that they have here, 270, 100, up to 390 watt peak. If you have to input, then you have to come to add new. And in add new, you would see it will ask you to add all of the parameters which we were talking about a while ago, which is the maximum power, the maximum voltage, the open circuit voltage, the maximum current, the open circuit voltage, sorry, and the short circuit current. These are the key things you need to add. If you have other parameters, again, like the number of cells, the area of one cell, etc., it will further fine-tune the electrical calculations that the system will do. But in principle, these first 5, the power, the maximum voltage, maximum current, open circuit voltage, and short circuit current, these are the key elements that you need, that we need. For Grundfos, again, as I was saying a while ago, inputting these parameters is a little bit challenging. I've not been able to navigate why. I tried asking a while ago, but I did not have a successful answer. So this is one of the limitations right now that personally I know we have for Grundfos when inputting solar modules. And once all of those are done, again, it comes on to us now to just click on sizing, and then it will give us all of the options that we have. Again, the optional sizing parameters, I will not go for, I will not put them, and that is it. Nonetheless, I would mention there was here in this place, if you want, and you have a particular brand of pump you want to consider, you can input the brand of pump here, for example, and it will calculate only based on this pump. So if you have only an SQF 1.2N, for example, you can do to select this, and then when the system will run, it will tell you later on whether or not this pump will be okay for your system or not, because you have given that as a condition that it must respect. Is that okay? But in principle, it's always advisable to leave it open so that you will have all of the all of the variety, and then the system will be able to choose for you the best one based on the properties you have input. Okay. Any question?
Olivia, now we need to close up a bit.
Yes, so 5 minutes, then I just show Lawrence. I'll be very fast. Anybody who would want to have more information, please, you can contact me or any of the other MSTs from Mogba, and then we'll be able to help you. 5 minutes, I just show you the presentation of Lawrence. I'm not sure what is showing on my screen. Can you see the compass software opening?
No, we still
No.
see Grundfos.
We're still in Grundfos.
Okay, so let me go to compass now.
Whoever needs Compass access, just write an email to your more closest MST or chat it on Yammer, and then we can facilitate that.
Voilà. Thank you, Maite. So can you see my screen now?
Yes.
Okay. So Compass, when you open Compass, as we said, it's a standalone, so you don't need internet and stuff compared to Grundfos. And remember, Lawrence is only solar. This is what it looks like. You have the option for submersible, for surface, and then for pools. We are interested in submersible. So we click here on the submersible. You have below here the different data sheets for all their products which they have, right? So of interest, we click on Lawrence. On submersible, sorry, and then you see it also has an illustrative image, and then this is all of the information you need to put. So in principle, we have to put, if we want a particular pump, we can select a particular pump here using custom. If not, we use all pumps that are available. And then Cameroon, Douala, again, another example. Yeah, remember what I said, the tilt angle, by default, it will assign the tilt angle based on the angle on your latitude angle that you have. By default, it will assign it. But you should always make sure that you check this to ensure that you have no issues. Here also, they ask you a percentage for dirt loss. You know this is for the solar panels, and you know if there is dirt on top of the solar panels, it reduces the amount of radiation it gets. So it asks you also for an idea of dirt loss, which can be 5%, 10%, depends on you and where you are. The motor cable, this will help you to define the area, the length from the pump to the controller, where you plan to put the controller. So you see on each of these things, when you click, it shows you exactly, it tries to annotate you on the curve, on the image, so that you should be sure of what you are inputting. Then, key point now and again is the total dynamic head, which if we have calculated before, we can put here the total dynamic head, and you see here we have the geometric height here, but you see that the pipe as well is highlighted, meaning that it has also taken into consideration, it considers the friction losses here. You get, so the vertical height from the dynamic water level to the highest point of delivery, plus pressure losses in the pipeline as height of water column. So what we were talking about, that is what is there. But if in this one you do not have it, we do not have it, then we click on pipe length, and then on pipe length, you see now here it has selected only the pipe, and it gives you what it asks you to enter: entire pipeline from the pump outlet to the point of delivery, right? And then you put this figure here, whatever it is. For our system here was 700, for example. And then here also we put the pipe type. Here they have made life a little bit easy. They have plastic, they have steel, and different kinds. And then they have the different pipe roughness coefficients out there. If you want to customize it, you can customize it with any of these ones, but this is up to you. I think I saw a hand. Yes. Who was that?
It's Rawlings. Yes. One question. Does the distance of the solar panel, for example, the point where you plant the solar panel to the borehole, does the distance affect the flow of current?
Affect the flow of current? Yes, that is why it asks you the distance of the motor cable here, because it has to be able to size as well the cable you will need, the size of the cable you will need, and we will see that in a couple of minutes. If you take a small cable, the cable can overheat, and then it will have huge head losses, and these head losses will cause that the flow of current to the controller does not work, or to the pump does not work properly, and then you have troubles. So yes, it's also a very important point. Thank you for bringing that up. Okay, so we do this, and then as I was saying, we select whatever we want to select here, whatever option we want to select here, and then this is what it is going to be used to calculate the total dynamic head. Then eventually again, the required daily output. Remember what we said, we are talking of meters cubed per day, and then sizing for average month, and etc., etc., etc. Here they have the option of limiting the flow rate. So if you want that to size it for a particular flow rate, you can put this option and limit it and stuff. So that's one of the options. But then remember about the generator, or the solar panels which we spoke about. Here we have to come and input the generator. So we come to PV generator tab, which is up here. And you see here, they also have just a couple of pumps that they have for their system, and then the rest you can customize it as you want. So for example, I chose a Remy 450. This is one of the pumps that I input by myself. So you take the peak, the maximum power for this solar panel, the maximum voltage, etc. You input them here. You just have to click on them and write. You click and you write the figure. You click and you write the figure, etc., etc., etc. So the more you have, the better. If you want to use all of these, you will have to select all of them. But if you want to focalize on what you have used, so that you're not calculating based on everything, you just select only what you need, and then halas, there you go. PV mount accessories, we will not look into that. If that is said, the same for the pump system. If you click on the tab pump system, it has all of the pumps that Lawrence has, or at least that my upgrade of the application has. And then it will calculate and choose the best pump within here. But if you want to choose just a particular pump, then you deselect all of them, and then you select just the pump you want to use, and then you can do your calculations. Once that is done, let's try it. Let's try for the example which we did. We are in Douala, tilt angle, this, etc. The pipe length was 700 meters. The required daily flow, I did not give the daily flow, but the required daily flow in this example, let's assume 300 meters cubed per day. And then let us assume sizing for a month with the least solar output. Then I will limit my flow to 30 cubic meters per hour, which is the maximum pumping rate of our borehole. I will limit my flow to that, and then I would click on calculate, and you would see it will spend a couple of seconds, and then it gives me this solution here, and it gives me all of this here, the pump size, etc. You'd see it gives me the pump the pump mark, model, the brand, etc. It gives me 19 times 3 solar panels. The same for Grundfos will show you the same. It gives me 19 times 3, so 19 solar panels in series, and then three chains of 19 panels. So a total of 19 times 3 panels, which you will need 19 in series, 3 chains in parallel. And then here you see you are talking about the solar, the size of the cable rollings. Here we have 4 millimeter square cable, a 100 millimeter pipe. The 100, this is the internal diameter. Pay attention. So it gives you that you need this diameter of pipe to go. And then it gives you all of the characteristics here. So for the month, the least solar output, this pump will be able to provide you 229 meters cube per day, right? Which is slightly lower than what we need, right? So below here, you would see also now on the curve, and this is what the solar systems do, because Grundfos as well does this. You would see if you go for this system, then in January, you would have 285 cubic meters. It is less than the 300 which we need. And all through the year, you can see. So now you decide whether or not you would want to go for this pump, or you would want to change your system characteristics. Or if you go for this, then you know that you would work for this during the solar pumping hours, which according to this, for Douala will go from approximately 7 o'clock, where we are pumping about 7 meters cube per hour in the morning, till about 5 o'clock in the afternoon, when we are pumping about 6 cubic meters per hour. And then you see the increase, the stability, and then the decrease, right? So if we decide to go for this option, then it means if we need to cover our 300 cubic meters per day, we will need to do this option plus generator pumping. Good thing, this pump that they have chosen here is a hybrid pump, so it can easily work with the generator and stuff. So that is a little bit how the system is. Now you can if you want to access more, you can see here, for example, this one has more power, more water, but it takes more solar panels. So you have to play between the pros and the cons of everything, try to do the cost estimates and assessments to see. So this one, the first system, it will give you, if you see here, the first system gives you 8.9 liters of water per watt peak of current, of power, sorry, right? The second one gives you 7 liters per watt, the third one, etc., etc. So it will classify all of these based first on this. Now it's left for you to see which one would be the best option you'd want to go for, and then you can pick it, or you can decide to change it. There is options where you can decide here will not change anything much. If you click on the upper arrow here, you will be increasing the number of solar panels, or you click on the down arrow, you will be reducing the number of solar panels, and you will be seeing what is happening in terms of the production here. You see. So if I increase, you see what happens, you see what happens. So you can also play with this, you play with this, and then you say, okay, I don't want to put 19 solar panels, 19 times 3 solar panels. I want to put only 18 times 3. This is what it gives you in terms of production, you see. So all of this, you can play with this. The same also for the pipe diameter. You can decide to increase the pipe diameter and see where it will take you and stuff. But at one point, you increase the pipe diameter, it will not change anything in the production, right? So you can also play with this. What I would want to show you is, if you take, you see the curve has this cell has become orange. Orange here meaning this is not very good. There's going to be a lot of friction loss, and this can lead to the breakage of your pipe if you take this diameter of pipe. And the more you reduce, you see it goes to red. Red, it means the system will not even work at all, you see. So these are things I just wanted to show you so that you should pay attention with, and then you can modify them. Similar thing for current and stuff. Voila. This has been a little bit fast, but I think you have seen and you have the principle. So this I would keep quiet here, and sorry for wasting your time.
Olivia, it wasn't a waste of time. It was very interesting, and I'm sure that people really enjoyed it. But it's a lot of things to do. I think the way we leave it, Olivier, is they've got the links, they know how to do it, they've been through it. So I advise them to go and play with it. Go and play with it and put some numbers in and see how you feel. And then you'll learn very quickly on the things that Olivier was showing you on how changing this will affect the choice of pump and things like this. So we have to close it off soon. You can say some last words, Olivier, if you want to say goodbye and some last words. I don't know how you want to wrap it up.
No, it is
Remind
fine.
them all tomorrow
Just
or
go,
when's the
you
next
play
one in
with it.
French?
If you have any questions, you come back to, you can ask me on, you can ask me any of the Western MSTs, and then I'll be glad to go through. Sahel, we can talk about this issue which you mentioned here, no problem. We can find the time tomorrow, we talk about it, that is fine. On Thursday, we would have the French session. So if there is somebody who will be interested again in the French, you're very much welcome. And voila, I'll be expecting questions. If you have questions you cannot ask now, please, you can still put them in the chat so that everyone can see. We'll try to answer them there. Or you write to me personally, we'll try to answer, or any of us, and voila.
Okay.
Shukran Kati.
Thank you very much, Olivier. That was a very comprehensive diving into wells and selection. So thank you very much, everybody, for attending. As Olivier said, please feel free to contact us if you need more information. And if you want us to go into any more subjects or any more areas you want us to talk about, or you want webinars and anything, please feel free to write to us and we can see how we can help you. So thank you very much for attending, everybody, and have a nice day. Thank you very much, Olivier.
Thank you. Bye-bye.
Thank you so much.
Thank you, Olivier. Thank you.